Good now, it's got a lot of angular momentum, right? If I just hold onto this rope, what's going to happen to the wheel? Right, it has all the angular momentum going, and some force, gravity is not enough to actually change it, right? Gravity's trying to pull it down, but that ain't enough. It's just... Right, I can change it. I can apply enough force and actually alter that direction.
Hello student, today we are learning as the law of conservation of angular momentum. Now before learning this, we have to remember that last year we learned that the law of conservation of the linear momentum. According to that law, the linear momentum remains the constant if the external unbalanced force acting on the body is 0. Now according to that law, we are finding here the law of conservation of angular momentum, and the statement of the law of conservation of angular momentum, which is similar to the previously law, but only the word is changed. Instead of the force, here rotational force is used, that is a torque, and instead of the linear momentum, angular momentum is used. Now if you see that the statement of the law of conservation of angular momentum, the angular momentum is conserved if the external torque acting on the body is 0 or it remains the absent. That is, mathematically we can say that the L is equal to constant if the torque is equal to 0. Now proof of this means we have to prove that the L is equal to constant, angular momentum remains the constant if the external torque acting on the body is equal to the 0. Now in that case, angular momentum of the system is the basic formula for the angular momentum. Vector L is equal to the R cross P. Differentiating this term with respect to the time, dl by dt is equal to d by dt of r cross p vector. Differentiating the two cross product of the vector, it will use the product value vector r cross dp by dt plus dr by dt cross vector p. Let dr by dt is the rate of change of linear displacement with respect to the time. That's why it is represented by velocity, which is equal to dr by dt. And the dp by dt in this equation is equal to the force, applied force. According to the Newton's second law, applied force is equal to the rate of change of linear momentum with respect to the time. Therefore, dp by dt is equal to the force. Both these values substitute in the previously equation. We get here dl by dt is equal to r cross f plus v cross p. R cross f plus v cross p value we substitute here m into v. And then taken as a m is outside of this bracket, inside of this bracket v cross v. Now this is the cross product of two similar vector quantity, and the cross product of two similar vector quantity is always 0. That's why this product gives as a 0 value. dl by dt is equal to r cross f. Now already we know the basic definition of the rotating force, that is a torque. Torque is equal to r cross f. Therefore substitute this value, dl by dt is equal to the torque value tau. Now if this tau is absent, means external torque is not acting on the body. If the body is rotating and the external force is not acting on it, that is the rotational force, tau is not acting on it, torque is equal to the 0, and therefore dl by dt is equal to 0. When the derivative of the term is equal to the 0, definitely we can say that the L is equal to constant, because derivative of the constant value is always 0. Then we get here the angular momentum is equal to the constant. Now see that the L is equal to I into omega. I is a moment of inertia and omega is a angular velocity. But we know that according to the law, L is constant, and this product remains the constant. It means that if the angular momentum goes on increasing, omega value must be goes on decreasing. Oppositely, if the I goes on decreasing, omega must goes on increasing. Now let us consider if there is a two systems are there. In that case, L1 is equal to L2. I1 omega 1 is equal to I2 omega 2. This formula is also we can apply for the problem solving. Next is that this angular velocity can be converted into the formula for the frequency, that is omega is equal to 2 pi n. Now substitute the value of it. I1 2 pi n1 plus I2 2 pi n2. 2 pi get cancel. I1 n1 is equal to I2 n2. And in ratio form we can write I1 upon I2 is equal to n2 upon n1. Example for this angular momentum is given by the ice skating, ballet dancer and driving in a swimming pool. Thank you.
Must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.